Hello. Today we're going to work on some of the preliminary theory for linear equations that are of higher order than 1. So up until now, we've been learning techniques, or I should say theory and techniques, for working with first order differential equations. In chapter 4, we go into working with higher order, so second order, third order, and so on. And we need to cover some of the theory beforehand. So keep in mind, in section 4.1, we are not learning how to solve any differential equations. We are merely learning some of the theory, okay? So in this section, when we cover the initial value problem, it's very similar to what we were doing before with first order differential equations. But now with an nth order IVP, we will have to have n initial conditions, one for each order of derivative less than the highest order. So for example, I've got here a second order differential equation. If it's second order, then I would expect to have two of the initial conditions, one for the zero order derivative and one for the first order derivative. And that is indeed what I have, right? So we'll use these initial conditions in order to find parameters. And our parameters are typically going to be called something like C1 and C2. Okay, now remember, we haven't learned how to solve these differential equations. Okay, so we'll be given solutions in this section and we'll be asked to do things with them. Okay, so for example, in the above IVP, where we have x squared y double prime minus xy prime plus y is equal to 0, with y of 1 equals 3 and y prime of 1 is equal to negative 1, the general solution is y equals c1x plus c2x ln of x. We're supposed to use the initial conditions to determine the values of the unknown parameters c1 and c2. Okay? Well, all we have to do is, for the y of 1 is equal to 3, we substitute 1 for x and 3 for y into the general solution. For the y prime of 1 is equal to negative 1, we need the derivative of the general solution. Okay, so we're going to have two steps here. We're going to be dealing with y equals c1x plus c2x ln of x, and the initial condition is y of 1 is equal to 3. That means 3 is, and I plug in 1 everywhere there's an x, so I get c1 plus c2 ln of x, but ln of 1, but ln of 1 is equal to 0, so this is just c1. So I automatically get c1 is equal to 3. That doesn't always happen. We got lucky with that one. Now I need y prime, so I need to calculate it. Y prime, if I take the derivative of y prime is c1 plus c2 ln of x plus c2x times 1 over x, which of course simplifies. This will be c1 plus c2 ln of x plus c2. Okay, where I just used the product rule with the x and the ln of x. The initial condition given is that y prime of 1 is equal to negative 1. So I'm going to let y prime be negative 1. That's equal to c1 plus c2 times ln of 1 plus c2. Again, the ln of 1 term goes to 0. And so what I'm left with is that c1 plus c2 is equal to negative 1. So we get c1 plus c2 is equal to negative 1, but remember we have that c1 is equal to 3. So we can substitute that in and continue on with our problem. So we have 3 plus c2 is equal to negative 1, which means c2 is equal to negative 4. So we found our parameters, and that's really what they wanted. Once we have the parameters, we can go ahead and express the general solution in terms of those parameters. So the general solution is then y is equal to 3x minus 4x ln of x. So not much different from what we did before. All right, now when we were working with the first order differential equations, we had that theorem for the existence of a unique solution, and we have that again. So let's read through that. If we let all coefficients of a differential equation be continuous on an interval I, and let the highest order coefficient, the a sub n of x, not be 0 for every x in that interval I, and if x equals x naught is any point in this interval, then a solution of the initial value problem does exist on the interval, and it is unique. So we're saying so long as we have an interval that all of the coefficients are continuous on, and the highest order coefficient is not equal to 0 for all the x's in that interval, then a solution of an initial value problem will exist on the interval, and it will be unique. This is easier than the first order. So if we were to consider the above IVP and apply this theorem, if we look at what that IVP was, there was an x squared in front of the y double prime, right? So that's the highest order coefficient, x squared, and x squared cannot be equal to 0, right? That's part of the conditions. And so this would mean that the solution to the IVP can either exist for x values that are greater than 0 or x values that are less than 0. Now, with our initial conditions being as they are, with x is equal to 1, that means the domain we would have for this particular IVP, so the IVP interval of definition would be from 0 up to infinity in order for it to contain those initial values. Okay? And then we know we get a unique solution. So that's kind of nice. We don't have to do anything too tricky. All right, let's see an example here. We want to find an interval centered about x equals 0 for which the given initial value problem has a unique solution. Okay? So our IVP is cosine of x, y double prime, plus sine of x, y is equal to e to the x. The conditions given are y of 0 is equal to 1 and y prime of 0 is equal to 0. So what we need to hone in on is the highest order coefficient, right? The theorem says that cosine of x, that's our highest order coefficient, cannot be 0. And so what this means is that x cannot be any of the odd multiples of pi halves. So we could look at plus or minus pi halves, plus or minus 3 pi halves, plus or minus 5 pi halves, and really in general it's plus or minus 2k plus 1 times pi over 2. 2k plus 1 is the generic way to write the representation of all odd numbers. Okay, and so we just want an interval centered about x equals 0, and that would be the interval with endpoints of minus pi halves and positive pi halves. So a unique solution will exist on this interval, minus pi halves to pi halves. It's as simple as that. Now you might be wondering, why did we choose an interval centered about x equals 0? The reason is because of the initial conditions. Y and y prime are both evaluated at 0. So any interval we choose must contain the value x equals 0 as well. Okay? All right, boundary value problems. Boundary value problems are very similar to initial value problems, although also quite different at the same time. So boundary value problem will be of second order or greater. The dependent variable, that's the, for us is typically y, and or its derivative will be specified at 2 different points. These points are called boundary conditions and are not the same as initial conditions. A boundary value problem may end up having several solutions, one unique solution, or no solution at all. And this is best illustrated by just walking through some examples with a solution that has several different boundary values, and then we can see what it looks like to have no solution or many solutions or any of the above choices. Okay, so I want you to take a look really quick. We've got an example, everything's written out, but I want you to look at these A, B, C conditions that are given. Notice that every single one of them is about y. So in part A, it's y evaluated at -1 is 0. Y evaluated at 1 is 4. So we're talking about, if you think about it on an xy axis, we're looking at from -1 to 1. Okay? And we don't care about, these values aren't both starting at the same place. That wouldn't make sense anyway. But we're talking about y of -1 being 0, y of 1 being up here at 4, and kind of, this is our little domain, right? And so each of these really is giving us just information about a boundary, not about necessarily an initial value, okay? So that's just something to keep in mind as we're going through here. These are not about initial values, they're about boundaries. So in our particular problem, we let y be c1x squared plus c2x to the fourth plus 3 be the solution to the boundary value problem x squared y double prime minus 5x y prime plus 8y is equal to 24. Determine whether a member of the family can be found that satisfies the boundary conditions. Okay, so we're just going to go through this, doing the work the exact same way we would with an initial value problem. We're going to evaluate the solution, y equals c1x squared plus c2x to the fourth plus 3 at each of these boundaries. So y of -1 is equal to 0. This tells me 0 equals c1, -1 squared is just 1, plus c2, -1 to the fourth is just 1, plus 3. So what I have here is c1 plus c2 is equal to -3. Okay, so far nothing weird. Y of 1 is equal to 4 is the next one. So that means 4 is equal to c1, 1 squared is just 1, so c1 times 1, plus c2, 1 to the fourth power is also 1, and then plus 3. So this one simplifies down to c1 plus c2 is equal to 1. Now, these two representations are the exact same on the left-hand side of the equal sign. We are saying, or these two things are saying, that -3 is equal to 1, which is very false. And the reason that they're both saying that is because on the left-hand side, they both say c1 plus c2, and that's called a contradiction. Okay, we have a contradiction. There's no way that c1 plus c2 could add up to be two different numbers. Okay, so there is no member to be found. And that's what it looks like. That's one of the ways it can look anyway. Yet two expressions that seemingly are the same, except they would give you a contradiction if you were to actually compare them. All right, let's look at the next one. In the next one, y of 0 is equal to 1. So that's saying that 1 is equal to c1 times 0 plus c2 times 0 plus 3. This is straight up saying 1 is equal to 3. That's totally false. And the reason it's false is it's a contradiction. I don't even care what y of 1 equals 2 gives me, because if one of the boundary values gives me nonsense, then it doesn't matter what the other boundary value is at all. I already have that there is no member to be found. In other words, there's no solution that could possibly satisfy those two conditions for both A and B. Let's look at part C and see what happens. In C, y of 0 is 3 and y of 1 is 0. So the y of 0 is equal to 3. This tells me 3 is equal to C1 times 0 plus C2 times 0 plus 3. Well, I get 3 is 3, which is a true statement. So I have no contradiction. But I also didn't get any information. I don't know anything about C1 or C2 yet. I just know that this could happen. So let's see what y1 of 0 gives us. Y of 1 equals 0. This tells me 0 is equal to C1 times 1 plus C2 times 1 plus 3, which means C1 plus C2 is equal to minus 3. I could solve for C2 in terms of C1. C2 would be minus 3 minus C1, but that is about all I could do. I could also just let C1 be C1. And in other words, what's happening here is I have an infinite number of solutions, and I could write up my solution, y of x, to be C1x plus, in the place of C2, I would put minus 3 minus C1, x to the fourth. I'm sorry, C1x should have been C1x squared. And then a plus 3 at the end. And that's about it. This is a member of the family that satisfies the boundary conditions, but there are, let's see, how did we put it up here? Several solutions, or an infinite number of solutions. So this is a member of the family of solutions. There are an infinite number of solutions because C1 can be anything. Okay. All right, so now we know what it looks like for there to be no member, and we know what it looks like for there to be an infinite number of members that are part of the family of solutions. Let's see what part D gives us. In part D, we're told y of 1 is 3 and y of 2 is 15. So the y of 1 is 3. This one tells me 3 is equal to C1 times 1 plus C2 times 1 plus 3, which again, I get that 3 equals 3 statement. Okay. No, I don't. Hold on. I'm sorry. I can't do math for just a moment. I subtract 3 from both sides. I get C1 plus C2 is equal to 0. That makes a lot more sense. Okay. In y of 2 is equal to 15, I get 15 is equal to C1 times 4 plus C2 times 2, 4, 8, 16 plus 3. So this tells me 4C1 plus 16C2 is equal to 12. If I divide everything by 4, this also means C1 plus 4C2 is equal to 3. Okay, great. I have a system of equations. In the first one, C1 plus C2 is 0, I could say C1 is equal to minus C2, and then I could substitute it into equation 2. So I'm going to replace C1 with minus C2, get minus C2 plus 4C2 is 3, so that's 3C2 is 3, and C2 is 1, which means C1 is minus 1. So y of x is equal to a negative x squared plus x to the fourth plus 3, and this is a member of the family of solutions. Okay, so we saw one of each at least, and two with the no members, just so you can see the couple of different ways that that comes up. All right, next topic. All right, the next topic, this whole section 4.1 is broken into 3 subsections, and this next one is about homogeneous equations, which we've talked about before. Homogeneous equations just means that the differential equation is equal to 0. That's it. So this guy right here in this linear differential equation form, where we have an nth order differential equation, the g of x that's on the right-hand side, that's going to be 0. That's the definition of a homogeneous equation. If g of x is not 0, then the equation is non-homogeneous. Okay? If our equation is homogeneous, then we have to solve this problem just one time, and we get the solution that's associated with the homogeneous equation. If our equation is non-homogeneous, then we're going to have to solve it twice. Once for the associated homogeneous solution, and another time for the non-homogeneous equation. So it'll be a bit more work, and we'll learn methods for these in other sections. Again, this section's kind of about the theory and the definitions and whatnot. So right now you need to know the difference between homogeneous and non-homogeneous. The order of the homogeneous differential equation tells you how many solutions you can expect. So if we have a second order differential equation, we'll get 2 solutions. Then we have this superposition principle. And it sounds really fancy, but all that it means is that I've got it down here. So let's kind of do this. We're going to take a little turn here. All that the superposition principle says is that if you have a couple of solutions to a homogeneous differential equation on some interval, then the linear combination of them is also a solution. So up here, I've written that as if we had 2 solutions to a differential equation, y1 of x and y2 of x, then the general solution would be the linear combination, where we'd get c1y1 plus c2y2, and that would also be a solution. And it'd be known as the general solution for the homogeneous equation. There are situations where we are solving our differential equation twice, as I said earlier, in the non-homogeneous case. And in those cases, we end up denoting the general solution there with a y sub c when it's dealing with the associated homogeneous equation. So I'm going to leave that off right now because this section is about the homogeneous equation. For some reason, my eraser is not working. There it goes. Okay. Let's see. One of the criteria that must be true for the individual solutions is that they have to be linearly independent. And a simple way to define what that means is that one of them can't just be a multiple of the other. So like if y1 is x squared, then y2 can't be 7x squared. That doesn't make any sense. Or if y1 is e to the 2x, then y2 is not going to be e to the 2x. Okay? We do not get repetitions of solutions. If we do, we have to fix them. And that's something that we'll learn in the next section, actually. One of the solutions that a homogeneous equation always has is the trivial solution. So the homogeneous equations always have the trivial solution, y equals 0. We typically do not list that as a solution unless it is the only solution. And I've been teaching this class a very long time and have yet to come across a differential equation that only has the trivial solution. All right, so I've already read the superposition principle, but let's look at an example of it. So if the 2 solutions for x squared y double prime plus 7xy prime plus 13y equals 0 are these horrible looking solutions, y1 is equal to 1 over x cubed cosine of 2 ln of x, and y2 is 1 over x cubed sine of 2 ln of x, And y equals the linear combination of them, where I just put a c1 in front of the y1 and a c2 in front of the y2, that is also a solution, and it is the general solution, so long as y1 and y2 are linearly independent of each other. So let's talk a little bit more about the linear dependence and independence, because I gave some examples like x squared and 7x squared. It's pretty clear that one is a multiple of the other. But it's not always obvious when two functions are linearly dependent, like one is kind of related to the other one in a big way. And so we need a way in order to determine that. And there's some theory that goes on behind this, and there's a bit of linear algebra that's doing its magic in the background. And I'm not going to go into all the details of the linear algebra that's going on here, because it's actually a very rich topic, and there's a lot to it. So I'll settle for what I've written here. A set of solutions is said to be linearly dependent on an interval if there exists constant coefficients, not all of them zero, such that when you add all of the solutions together with c's, you would get back zero. Let's see why that is, though. So I could play with this equation where c1y1 plus c2y2 plus all the other guys plus c sub n y sub n is equal to 0. And I could simply say, you know what? I'm going to move everything except c1y1 over. Well, then c1y1 of x would be written as a linear combination, negative c sub 2 y sub 2 of x plus minus all the guys in the middle minus c sub n y sub n of x. What this is saying right here is that y1 of x can be written as a linear combination of all the other solutions, which would mean that it's dependent on them, right? Because it can be represented as a linear combination of the others. So this would be a dependent situation. If the set of solutions is not linearly dependent, then they are said to be linearly independent, which is what we want, okay? This method of like seeing if you can add up all of your solutions and get back zero is not how we want to actually figure out independence. That is merely a definition. If we can look at two solutions and see that they're constant multiples of each other, then that's an easy explanation. If we see, if, for example, we have three solutions and one of them can be written as a linear combination of the other solutions and you can easily determine them, then that's great, go for it. But in general, we want a way that works for all functions that doesn't cause a lot of grief trying to figure out whether we can write them in terms of each other or not. But in order to do this, we first need to learn a little trick. It's a tool actually called the determinant. You may or may not have seen it. But we have to learn it in order to be able to determine dependence and independence easily. So the determinant is an operation or a tool that we apply to a matrix. And a matrix is just a way for us to represent the coefficients or functions or many different things. It's an organizational method of elements by rows and columns. So if I have a 2 by 2 matrix, it's 2 rows and 2 columns, and the components in it are A, B, C, D, and I call it A, then the determinant of A is denoted with what looks like absolute value bars on the A. Or you could just write det of A. Either way is totally sufficient. And the calculation of the determinant is kind of like a cross product. We start at A, and then we go down to D, and we get a product, A, D. And that is a positive product. Then we start at C, and we subtract, and we go up the diagonal to B, and we have BC, okay? And so we're going to get AD minus BC. And that's always the order. We always start at the top left corner and take the diagonal down and multiply. And then we subtract starting at the bottom left corner and take the diagonal product, okay? So if I had something, for example, like, let's see, I'm going to do numbers for now. So let's say I had 2, 3, -4, -5, something like that. Okay. I've already put it in the bars in order to show that I'm going to calculate the determinant. So I need a positive diagonal product minus a diagonal product. So I've got 2, this is equal to 2 times -5 minus a -4 times 3, which is -10 plus 12, which is a +2. Okay, not too hard. So then we have to move up to the determinant for a 3 by 3 matrix. And a 3 by 3 matrix, we have 3 rows and 3 columns. And the determinant that we calculate here requires that we break down the 3 by 3 determinant into a sum and difference of 3 2 by 2 determinants. We start at the top, at the first row, first column with A, and we isolate the column and row that A is in. And what's left behind is a 2 by 2 matrix, EFHI. So I'm going to take A with a positive sign and multiply it by the determinant of what's left behind when I delete the row and column that A is in. Okay, and that'll be a 2 by 2 determinant using the same diagonal product that we used in the 2 by 2 up above. Once I have dealt with A, I move on to B. Circle B, cross out the row and column, the row and column that B is in, and put a minus sign. We always alternate signs, okay? So we get a minus B times the determinant of the elements that are left behind, which is going to be D, F, G, I. Okay? We stick those into a 2 by 2 determinant, and then we're going to calculate that diagonal product on that 2 by 2. Then we move on across that first row to C, and we already did plus minus or back to plus. We delete the row and column that C is in, and we take C and multiply it by the determinant of the remaining elements, D, E, G, H. And then we have that diagonal product to calculate the 2 by 2 determinant that's left. In the end, we're going to calculate a whole lot, and it'll be really easy to make mistakes because of signs. Doing any work in your head is really not recommended because of this. And if we were dealing with numbers, that's one thing. We're going to be dealing with functions, but I'm just going to do one quick little example where I have, I'm going to calculate a 3 by 3 determinant. And I'm just making up numbers here. I've got 1, 2, 3, 0, 4, -1, 3, 2, 2, something like that. Okay. So I'm going to follow the directions that I gave you to begin with. I'm dealing with 1. I kind of just imagine that I have deleted the column and the row that 1 is in, but I can put in the highlight in there for now. So the determinant will equal 1 times the determinant of the 2 by 2 with elements 4, -1, 2, 2. And then I erase that. And I go to the second, the B, and I erase the row and the column that it is in. Remember, I have a minus sign, so I get -2 times the 2 by 2 determinant of the remaining elements, 0, -1, 3, 2. And then that part's done. And so I move on to 3. Delete the row and the column that it is in, and I'm switching to a plus sign. I'll just leave my plus minus plus across the top. And that's +3 times the 2 by 2 determinant of the remaining elements, 0, 4, 3, and 2. Okay, so now I'm going to go ahead and do those diagonal products, calculating my 2 by 2 determinants very carefully. This will be a 1 times 4 times 2 is 8, minus 2 times negative 1 is a negative 2. Minus 2 times 0 times 2 is 0, minus 3 times negative 1 is negative 3. Plus 3 times, and I get 0 times 2 is 0, minus 3 times 4 is 12. This becomes, it looks like 8 plus 2, which is a 10, minus 2 times 3, plus 3 times negative 12. This becomes 10 minus 6 plus, or not plus, minus 36. Okay, that'll be minus 42 plus 10, which is a negative 32. That's it. I just get a number. And right now, with just some generic 3x3 matrix full of numbers, that value, negative 32, doesn't tell me anything. The determinant is a tool. It gets applied in different situations and has different meanings depending on the situation. We're going to use it for independence, to test for independence. So if we're considering solutions of a differential equation and we want to try to determine if they're linearly dependent or independent, we're going to use the Wronskian to make this determination. And the Wronskian uses the determinant. Okay, so suppose y1, y2, and y3 are solutions of a third order differential equation. The Wronskian, or so the determinant, the Wronskian of y1, y2, y3 is equal to the determinant of this 3x3 system, where notice the first row is y1 with its first and second derivatives. The second row is y2 with its first and second derivatives. And the third row is y3 with its first and second derivatives. How do I know how many derivatives to take? I go until I have a square matrix, 3x3. I didn't just want one derivative because that would have given me 2 rows. I have 3 columns. I want 3 columns and 3 rows. That's how I know when to stop. If the Wronskian is equal to 0, then the solutions are linearly dependent. And I want to include here that this is for any x. So if there's one value of x that would make that Wronskian equal to 0, you've got dependence. Okay? If the Wronskian is not 0, then they're not dependent. And it has to be true for every x. And then we have linearly independent solutions. Once we know that we have a linearly independent set of solutions, then we can say that they form a fundamental set of solutions. Okay? So linearly independent solutions can form a fundamental set of solutions. And once we know that our solutions form a fundamental set, then the general solution to the homogeneous differential equation is just a linear combination of those members from the fundamental set. So let's look at an example. Determine if the solutions are linearly independent and thus form a fundamental set. If they do, form the general solution. Notice there's no differential equation here. We don't need the differential equation to talk about dependence and independence or to form a general solution. We just need the solutions. So let's do this. We're going to look at the Wronskian of e to the 3x, because that's y1, and y2 is e to the minus 4x. This will equal, so I write out my determinant bar. Across the first row, I put each of my solutions, e to the 3x and e to the minus 4x. And so I only have 2 solutions. That gives me 2 columns, which means I just need 2 rows, which means I only need the first derivative. The first row, or first column, the derivative is 3e to the 3x. The second column derivative is minus 4e to the minus 4x. I get my diagonal product, and it's going to be negative 4e to the 3x e to the negative 4x minus 3e to the 3x e to the minus 4x. I got to simplify that. This is equal to negative 4 e to the minus x minus 3 e to the minus x. and that is equal to a negative 7e to the minus x. Now, e to the minus x is never 0 for any x in the real number system, right? You can raise e to any number out there and you will never come back with 0. The exponential function has a horizontal asymptote at 0, so that means we're safe. And because the Wronskian does not equal 0, we say y1 and y2 are linearly independent. And then we say that, let's see, the fundamental set of solutions, because we were asked for that. So the fundamental set is, got to use set notation, with e to the 3x, comma, e to the minus 4x. And then the general solution is y equals c1 e to the 3x plus c2 e to the minus 4x. And that's it. So 2 by 2 is not bad. The calculations are pretty straightforward. Let's look at when we have 3 things and see what happens. Okay, so in this case, we're given 3 solutions. y1 is 1 plus x, y2 is x squared, and y3 is x. So we are going to calculate the Wronskian of y1, which is 1 plus x, y2, which is x squared, and y3, which is x. So I form my determinant. Across the first row, I list each of the functions, 1 plus x, x squared, and x. Because there are 3 columns, I need 3 rows, which means I go up to 2 derivatives. In the first column, the first derivative is 1, the second derivative is 0. In the second column, the first derivative is 2x, the second derivative is 2. In the third column, the first derivative is 1, the second derivative is 2. Okay, so now I can go ahead and calculate what my determinant is going to be. And I have to do that thing where I focus on the first element. I got the 1 plus x, and now I'm going to really just imagine crossing out the row and column that it's in. And so then my determinant is equal to this, in parentheses, 1 plus x times the determinant that has components 2x, 1, 2, and 0. Then I move on to the second column, and remember I have a minus sign. So I get a minus x squared. Imagine that the column and row it is in are gone, and the 4 remaining elements are 1, 1, 0, 0. And then finally, we get to the last one, x. So we get plus x. Imagine the row and column it's in gone, and then the remaining elements are 1, 2x, 0, and 2. Okay, so now I do my 2 by 2 calculations on each of these 2 by 2 determinants. And I have my 1 plus x in parentheses times 2x times 0 is 0, minus 2 times 1 is 2, minus x squared, 1 times 0 is 0, minus 0 times 1 is 0, so the middle term is going to go away, plus x times 1 times 2 is 2, minus 0 times 2x, which is 0. Okay. This simplifies to be minus 2 minus 2x plus 2x, which is equal to minus 2. And minus 2 does not equal 0 for any x in the real number system. Minus 2 is just minus 2. So we're safe there. And because w is not equal to 0 for any x, the solutions are linearly independent. And then we can form a fundamental set. And the fundamental set is just going to be this, use set notation, and we're going to place each of the solutions in there, the 1 plus x, comma, x squared, comma, x. Okay, and then the general solution can be formed from members of the fundamental set. And it is y of x equals c1 times the quantity of 1 plus x plus c2 x squared plus c3x. And that's it. And that also finishes up homogeneous equations. Okay, so there's a little bit of theory in there to be aware of. Number one, that superposition principle. Number two, the existence of a unique solution, and then the linear independence or dependence that could happen. The last section of this section is non-homogeneous equations. So when we deal with non-homogeneous equations, this is the situation where g of x is not equal to 0. And so we're going to deal with a situation where we have two solutions to search for. One is called the complementary solution, and it'll be found the same way we do when we have g of x equal to 0. The second solution is called the particular solution, and there will be various ways that we find that one. Okay, so solving the associated homogeneous equation for a non-homogeneous linear differential equation results in the complementary solution. We always use the notation y sub c to indicate the complementary solutions to the homogeneous equation. If you just write y equals, y is reserved for being the general solution. And so we don't want to use just plain old y. We need to use y sub c so that we know which solution you're talking about. We'll have to solve for the unknowns, those c1, c2, and so forth, using initial conditions if they're given, but only once we have the general solution. Okay? Solving the non-homogeneous part of the non-homogeneous linear differential equation results in the particular solution. We always use the notation y sub p to indicate the particular solution to the non-homogeneous equation. But notice, with the complementary solution, we had c1y1 plus c2y2 and so on and so forth. For the particular solution, we do not use little c's. We use big capital letters straight from the alphabet, A, B, C, D, E, F, G. If there is a capital letter that you should avoid writing in the midst of numbers, then don't use it. Like for me, I think D's are bad because sometimes they look like zeros, right? So I might skip from C to E. They're just unknowns, okay? We will have to solve for the unknown values of A, B, and C by taking our particular solution and plugging it into the differential equation and then using a process called equating coefficients. It's a bit of work, and we'll cover that in a few sections. Okay, right now we're still in theory. So according to the superposition principle for non-homogeneous equations, it's the same as when we're dealing with homogeneous equations. Any solutions we get to our differential equation, their linear combination should also be a solution. So what I mean by that is that the general solution is the linear combination of the complementary solution and the particular solution. And then once we have that, we can apply any initial conditions if any were given, and then we'd be done with the problem. Okay? None of this told us how to solve a non-homogeneous equation. All it did was just give us some definitions. Okay? And state that we're going to have to solve the associated homogeneous and the non-homogeneous diffie-q. All right, one example that is similar to what you might be asked in homework. You will get asked to verify that a given two-parameter family of functions is the general solution of a non-homogeneous differential equation on an interval. We're given the differential equation y double prime minus 7y prime plus 10y equals 24e to the x. And we're given the general solution, y is equal to c1 e to the 2x plus c2 e to the 5x plus 6 e to the x. And we're supposed to verify it. Before I verify it, I just want to point out real quick that the c1 e to the 2x plus c2 e to the 5x, that is the complementary solution. Okay? I see C1s and C2s, I automatically start thinking that came from the associated homogeneous equation. The 6e to the x, that was from the particular solution. So they have formed a general solution with the sum of the complementary solution and the particular solution here. We don't need to know that for what we're doing. I just wanted to point it out. That's all. Okay, to verify a solution, plug or substitute the given y and its derivatives into the differential equation and make sure equality holds. That's it. Very similar to when we checked solutions back when they were just numbers, just quite a bit more work. Okay, we have y is equal to c1 e to the 2x plus c2 e to the 5x plus 6 e to the x. So y prime is 2c1 e to the 2x plus 5c2 e to the 5x plus 6 e to the x. And y double prime is 4c1 e to the 2x plus 25c2 e to the 5x plus 6 e to the x. These are what I'm going to substitute into the differential equation. So y double prime minus 7y prime plus 10y. I substitute these in probably quite different than you might think. So this is equal to, all right, I've got to plug in y double prime, so that's 4c1 e to the 2x plus 25c2 e to the 5x plus 6 e to the x. Then I'm supposed to do minus 7 times y prime. I write it directly below what I wrote for y double prime, and I distribute the minus 7 right away. If I distribute a minus 7 to y prime, I get minus 14 c1 e to the 2x minus 35 c2 e to the 5x minus 42 e to the x. Then I have plus 10y. I'm going to write that directly below where I wrote the minus 7y prime, and I'm going to distribute the 10 through to my y. So I get plus 10c1 e to the 2x plus 10c2 e to the 5x plus 60 e to the x. And then I add them together to see what I get. Okay. And the nice thing about writing it this way is I don't have to hunt for like terms. I have them lined up for myself, and I do recommend this strategy in this class. Very much so. So in the first column, I have 4c1 e to the 2x. I have a positive 10 of those, and I have minus 14 of those. I get 0c1 e to the 2x. Similarly, with the second column, I have 25 plus 10 minus 35. That's plus 0 c2 e to the 5x. And then I have 66 minus 42. So let's see. Math is hard. That's going to be 24. Yeah, that'll be plus 24 e to the x. Okay, is that what the original differential equation was equal to? Yes. So this equals the original right side of the differential equation. Okay, so the function that was given is a solution to the differential equation. because when we plugged it in, our equality held. Okay, this is all that I've got for you. If you have any questions at all on any of the material, please reach out.